Chapter 15 and 16, slides 26 to 51. So far, we have discussed a few different spectroscopy methods: infrared spectroscopy, how to look at functional groups; UV vis. We're not going to really look at the spectrum of a UV vis. I just wanted to let you know what that was all about and that we can identify wavelengths for given conjugated compounds. Not super helpful when we're trying to figure out what a molecule looks like, though. Mass spec is super helpful, but it's a spectrometry, not a spectroscopy method, that helps us identify somewhat structure, mostly molecular mass and/or formula. We're now going to look at nuclear magnetic resonance. The advent of the NMR, for short, has been groundbreaking relative to speed. Using to run an NMR is actually very fast, and also the vast and rich amount of information that NMR spectroscopy lends us. Now, the key here is that this instrument has a lot of different functions. In fact, I could teach an entire 2-semester course on NMR spectroscopy alone. So we're just going to touch upon a little bit about how it works and the basics of reading a more simple spectrum. So it's important to understand that we're actually going to get some connectivity information when we run an NMR. And I want you to be aware that we are going to be focusing on Proton Nmr, or H1, right? Proton Nmr. Now, the instrument has the ability to probe other atoms, and we'll talk about those a little bit later, but I want to focus on the fact that we're going to set the instrument. It's called tuning it. We're going to tune it to the H1 atom, to the protons of my molecule. So we're going to get the instrument to only talk to us about what it sees relative to the hydrogens, the protons, the H1 atoms on any given molecule that I put into the system. Now, it's also important to understand that nuclear magnetic resonance is actually the same as MRI. If any of you guys have gone and gotten an MRI, you have been put into an NMR. You were the sample and you were put into a large magnet and you were, that sample. What we're doing is the same thing. We're taking a pure sample of our compound and placing it into the instrument, and the instrument itself has a huge magnet. So what is happening? Oh, well, a little bit of history too. The reason why they changed the name from NMR, nuclear magnetic resonance, to MRI, magnetic resonance imaging, was because putting someone into a large cavernous claustrophobic space and using the word nuclear freaked everyone out. So people, people who don't know much about science and things of that nature were being told they're putting into a nuclear instrument. Nuclear. Now they were getting confused in the terms. When nuclear magnetic resonance is because we're actually affecting the nucleus of the atom. It has nothing to do with, nuclear bombs or anything, but the public freaked out a little bit. And so they took the word nuclear out, right, of NMR and just kept the MR and then added the I, MRI, magnetic resonance imaging. But it's the same principles. Now, how does an NMR work? I'm just going to spend this slide talking to you a little bit about what's going on, because in the other cases with infrared, it was, kind of easy, or UV vis, it's kind of easy. You put it in an instrument and you take something that can make that energy infrared energy or UV vis energy, and you shine it at the molecule. So they're actually not super complicated instruments. NMR, farther up in cost, we have two of them at RIT. One is a 300 megahertz NMR, and that's based on the size of the magnet. We also have a 500 megahertz. These go way up in cost. NMR instruments are, costly to also run. They have to, the magnets have to be cooled with liquid helium and liquid nitrogen, and that is costly and has to be done weekly on a schedule. So there's a lot to them, okay? But let's touch upon the most widely used experiment run on an NMR instrument. I'm going to start with a sample. If you take a look at the sample right here, it is a ketone with a methyl group on one side and an ethyl group on the other. Now I've highlighted the hydrogens to point out that this instrument, we're going to tune the probe and we're going to tune it so that it sees the hydrogens on this molecule. It doesn't see the carbons, it just sees the hydrogens. Now what's happening? Imagine you've got a sample and it's in solution and these molecules are floating all over the place. So these hydrogens on the sample, they're little s orbitals, right? They're kind of like their own little Earths and they're spinning on their own axis. So that's what this representation in the middle here is. Imagine these hydrogen atoms are like spinning orbs, like little planets spinning on an axis. And there's a pole. There's a north pole and a south pole. So they're creating their own little micro magnetic environments. But they're all random because you have this sample in solution. So they're all just random motion and different. They're spinning one way and spinning another, and they're all just, there's no order to them. Then you take your sample and you place it right in between here. This is where the sample goes, and it's in the magnet. It's in this massive magnetic field. That's the instrument. So we have these they're like huge, monstrous instruments, and you take your little sample and you put it inside, and it embeds your sample right in the middle of the magnet. So now you've just introduced a huge magnetic field, an external magnetic field. That's B sub O. So the magnetic field, there's a north pole and a south pole. And so what happens is that suddenly all these little magnets, the hydrogens, which are probed by the instrument, they are aligning, or maybe you have a couple that go against the grain that are higher. So you have these alpha and beta states, these low energy, because they're going with the magnet, right? They're going with the magnet. And then you might have a couple that are against the grain, just they've aligned, they've organized themselves, but oops, they're against the magnet. They're in a higher state. Okay, so that's what happens when you just introduce the sample into the magnet. They all suddenly go from random to, standing at attention with the magnet. Kind of like a sergeant. All right, attend, hut. Everybody in line. Okay, everyone's aligned, or maybe a couple misaligned. Next, this is where the energy comes in. This is where the spectroscopy part happens. Okay, what's the energy we're going to use? We're going to use radio frequency. We're just going to pulse radio frequency at these protons, or at the sample, and then we're going to remove that radio frequency and let relaxation occur. So you can see that when we hit it with radio frequency, we're not ejecting electrons from, one shell to another. We're not changing valence electrons. We're not changing the electron configuration of anything, not like those high energy methods do, right? Like UV or X-ray. No, we're just using a very, very, very low energy radio frequency. This is even way lower than infrared. And all that's happening, they're not even vibrating, right? The molecule's not even doing its IR dance. No, all that's happening is that some of those hydrogens, which were aligned with the magnet, they all sort of jump to a higher energy state. So they maybe flip and misalign. And that's what's happening right here. But after relaxation, everything goes back to its normal low energy state. Their original alignment. Once you take the radio frequency energy away, they all sort of realign with the magnet. Okay, so what's that going to do? Well, there's a lot that goes in behind this black box, okay? Like I said, I could spend an entire year talking to you guys about NMR spectroscopy and all the varied things you can run on it. But the long and short of it is summarized in number 5. So what happens during that relaxation is that the signal is converted to a spectrum by Fourier transformation, or FT. The amount of radio wave energy necessary for the alpha to beta energy transition, that's the low energy, high energy state, transition, it depends on what type of environment the hydrogens are in. Are the hydrogens on a carbon immediately next to the carbonyl, or are they a little bit further away from the carbonyl, right? Like the hydrogens on the far right. When the alpha spins are flipped to beta spins, the atoms are said to be in resonance. And that's what we were looking at in the previous, right? The alpha to beta flip. The use of the term resonance here, I do not mean it to mean there's resonance happening like we did in the UV vis with conjugated systems. This is more of the physics term. The use of the term resonance is totally different because we're talking about electrons and molecular orbitals, okay? It's different from when we were talking about UV vis. This is going from a low energy to a high energy flip state. That's when they're called in resonance. So it means something different, unfortunately. Now, what you're getting is over time, you're getting the emitted energy that's recorded over time. So you hit it with the radio frequency, they flip their spins, we would let them relax, and we watch what happens over time. This is called the FID, or the free induction decay, and it's recorded over time. This is mathematically converted to frequency using Fourier transform. And this spectrum down here is exactly what we get at the end of running a Proton Nmr. That's what a Proton Nmr looks like. You'll notice that the baseline is at the bottom. And you'll notice that there are 3 groupings of things. I don't know, there's a group here, and there's something here, and then there's another grouping here. These are called signals. There are 3 signals that I see. They have different shapes and splits and stuff, but there are 3 different signals that I'm seeing. And they're on a baseline, and we're only really reading the x-axis in parts per million, and this refers to the frequency. Okay, we're going to learn a little bit on how to decipher what is this is a very packed in bit of information. What do we read from an Nmr spectrum? Okay, well, as I mentioned, that we're probing the H1 protons. And I just want you to note that you can do a carbon-13 Nmr, you can do an N15 Nmr, an F19, or a P31. There are other atoms that you can set the instrument to probe, but the most widely used is the proton. Why? Well, when you're working with organic molecules, there's a heck of a lot of them. And not only that, it's also the natural isotope, right? So if it can only see the natural isotope, which is in 99% abundance, you're going to, the likelihood of you seeing all of the hydrogens on every carbon is very high. Note that if you were interested in running a carbon-13, you need a lot more sample, because think about carbon-13, that is not the natural isotope. So you have a lot of molecules in there, but maybe not every carbon in the molecule could ever at one time be a carbon-13. And so you have to actually use a greater concentration of sample when you're doing carbon-13 Nmr. And it's a little less informative. Combined with Proton Nmr, it gives us a lot more information. So we're going to focus on Proton Nmr because you don't actually need much sample. You could run it on 1 or 2 milligrams of sample and get a beautiful Nmr. So let's just focus on those red protons we see. There's a lot of things to unpack from this spectrum, and these are the questions that we're going to go through methodically. Does it matter how many, I should change this word to how many signals. Let's change this word to signals. Does it matter how many signals there are? Yeah, it does. We see 3 signals in this particular spectrum. Why do we see 3? Does it matter how high the peaks are? Like, why is this peak higher than this peak, right? What does that matter? And it does. It's called integration. What about the splitting patterns? Why does this one have all of these little peaks off of it, while the one in the middle just looks like one tall peak? That's called multiplicity. We're going to talk about that as well. And the last thing is, does it matter where they are on the graph? Like in the parts per million, why do you see the peak at 1 ppm and then there's one at like 2.1 ppm and then why is one at like 2.5 ppm? Like, so where they are on the scale, the frequency domain, what does that matter? This is called chemical shift. Each one of these things tells us something and adds to the support for what the molecule must be. So I've listed up in the top corner in blue those 4 questions, right? The number of signals, chemical equivalence, the signal location, chemical shift, ppm, signal area, the integration, like the tallness or the shortness of the peak, and splitting pattern, multiplicity. So let's go through each one of these step by step. We're going to start with chemical equivalence. This is the how many hydrogen environments are there, or why do I see 3 signals? When you're looking at a molecule, take the molecule that we're looking at in the center, this ketone here. Hydrogens on the same carbon that can average the same environment only produce 1 signal at a given frequency. What does that mean? Well, imagine a Ferris wheel, okay? Imagine that this carbon is a Ferris wheel, and it's got seats to each one of the hydrogens off of it, okay? So if you ever walk up to a Ferris wheel and say, I want that seat over there has a better view than all the rest. Like, no, that's not the case, right? Because a Ferris wheel is, if it's a good one, hopefully, you get on the Ferris wheel and hopefully every seat on the Ferris wheel averages the same view because you're going round and round and round. So if you think about it, all of the hydrogens on carbon 1, we'll say, are equivalent because of the rotation of that single bond, we average the same view. So it doesn't matter if I was this hydrogen, HA, or the next one. So let's call all of these hydrogens, since they're equivalent, HA. The next area of equivalency is this carbon, right? This carbon has 2 hydrogens on it. And because of, again, single bond rotation, over time, one hydrogen, the hydrogen at the top that I have right up at the top here, if it looks left and right, it sees a carbonyl on one side and the other HA on the other. You might say, well, the one on the bottom doesn't see the carbonyl next door, but it actually does. Why? Because they're averaging the same view. They're on a Ferris wheel and all of these bonds are rotating. And so they are really equivalent. When they look out their window, they see the same view. So we're going to label those as the second environment. Each one of these will be labeled B, arbitrarily. The only other environment we see is the far left, right? The carbon on the far left has 3 hydrogens, and we'll call these C. Now, you might say, well, why didn't we call them A? Well, the hydrogens in environment C are on a carbon immediately next to the carbonyl. So it's almost like degrees of separation, right? HC is on a carbon next to a carbonyl. HA is on a carbon, 1, next to a carbon, 2, next to a carbonyl. Those are not equivalent environments. Carbon 2 on one side is in a neighborhood that has 3 hydrogens, right? It's next to a carbon with 3 hydrogens, next to a carbonyl. So it's like you ask yourself, are there any hydrogens like that living in that neighborhood? So I like to think about it as the carbons are houses and the hydrogens are the people living in them. If you are hydrogen B living on a C2 house, are there any other houses that have the same exact neighborhood as you? A methyl on one side and a carbonyl right on the other. I mean, look at the totality of the groups on either side of you. There's nothing like being in carbon 2, right? So HB is its own people living in that house, their own environment. Same thing for HC. HC doesn't have any neighbors on one side, but it's immediately its carbon next door immediately is a carbonyl. So we're going to bring this neighborhood and houses back a little bit later. But this is what gives us three different signals. So each one of these signals, this is a signal, this is a signal, and this is a signal. So there are three signals. But which one is which? Okay, so how many unique hydrogen environments there are will dictate how many signals you see. That's the first thing. Here are some more examples trying to get you to understand chemically equivalent protons. If you look at 1-bromopropane, which is drawn down here, you can see that it's indicated that it has three different signals. The CH3 on the end, these hydrogens, there's nothing else like them. Look at them relative to the bromine. It's a very asymmetric molecule. So we're going to call those A. Right? Here's hydrogens at A. There's no other hydrogens that are on a carbon connected to a CH2, connected to a CH2, connected to a bromine. Then you have hydrogens at B. These two hydrogens are on a carbon, where on one side it's got a methyl, and on the other side it's got a CH2Br. They are in their own environment. So they are, we'll call them arbitrarily, B, environment B. And then we have another CH2. This CH2, the hydrogens on that carbon have the bromine directly off of it. There's no other hydrogens living in a house called carbon with a bromine directly off of it other than those two. So we'll call those C. Those hydrogens are the only ones that are probed, and there are going to be three signals on an NMR because of three different chemical environments for hydrogen. What happens when you have a symmetric molecule like this one? This is 2-bromopropane. 2-bromopropane has a CH3 here. So that's a CH3. These hydrogens are on a carbon directly connected to a carbon bearing a bromine and a methyl. You could say the same sentence for the methyl on the other side. These three hydrogens on the left are connected to a carbon, connected to a bromine with connected to a carbon with a bromine and a methyl off of it. And so these two environments are the same. These hydrogens and these hydrogens are the same equivalent. They see the same thing when you look at their patterns. Then there's one assumed hydrogen in the middle, and there's nothing else like it. That hydrogen is on a carbon with the bromine on it, and there's no other hydrogen like it on the molecule, so we're going to call it B. So you would see two different signals, signal A and signal B for that molecule. Have a look at these molecules and understand why you would only see one signal for this ether, because the two methyls on either side are symmetrically equivalent and symmetric. You would see a methyl here as its own environment. We'll call it A, or actually we'll call it B, just like in the, and then there's a carbon in the middle here, but it doesn't have any hydrogens off of it, so that's fine. But then all of these are methyls, and these methyls are environmentally the same. They all are connected to the same carbon with the same pattern off of it. So these are all considered equivalent. Same thing for the top one. You have a methyl on the end. It's 2 away from the oxygen, so it is not equivalent to the methyl directly attached to the oxygen. And then you have the 2 hydrogens on this middle carbon, so you definitely have 3 environments, A, B, and C. So that's going to tell us how many we have. Now, remember what I said about rotation. Two examples of when rotation kind of makes things a little tougher to see relative to equivalent views. Take this ether, for example. We have a methyl to an oxygen to a CHCl2. We have got the methyl on the one side is in its own environment, and the hydrogen on the right is definitely in its own environment. So we're going to see two signals for that. Now, the CH3 on the left, all of those hydrogens on the carbon are equivalent because you have full rotation around the single bond. What happens when you have a double bond and you don't have free rotation? So take a look at the hydrogens on this methyl group. We do not have free rotation around the double bond. So that methyl group sees right across the way, it sees a hydrogen. And then on the other direction, on the same carbon but across the way, it sees a methyl. That methyl is actually equivalent to the methyl on the other side because look at its view. The methyl down below looks across the double bond and sees a hydrogen and then looks back and sees a methyl. So we can actually, because of symmetry, we're going to see two signals, even though there is no rotation in the middle. Okay, let's change it up a little bit. What if I had a carbon-carbon double bond, but look at it now. It is not symmetric. It's not a symmetric molecule. So, because we don't have rotation, the A is stuck, seeing what it sees. A sees a hydrogen across the way, and then when it looks down, it sees a hydrogen across the way. HB, when it looks across the way, sees a bromine, and when it looks back, sees a hydrogen. So that's a different view. HC sees a hydrogen across the way, and a bromine immediately on the carbon attached to it. So it's a different attachment point. So that's like a different view set as well. I can put it in a different color. Sees a hydrogen across the way and a bromine straight down. So you can see that each hydrogen has a completely different frame of mind, frame of view, because it's set. Had that been a single bond in the middle, there would have been rotation and the views would have been averaged. You would have gotten the same view. But because you can't rotate cis and trans double bonds, the hydrogens are set and they look out their window and they always see the same view. There's no averaging view. So when you have rings, we see this similar thing. You can't rotate around a ring. The ring is kind of set. And so hydrogens on one face of a ring versus the bottom face of a ring on average will, top face of the ring, bottom face of the ring, they might see different things. And so you get these complex signals or splitting patterns depending upon the rotation or lack thereof in a given molecule. Here's benzene. If you have a very symmetric molecule, look at benzene. Every hydrogen is equivalent. If you substitute one group on the benzene ring, now we have different environments. Your symmetric relationship to the nitrogen, right? The hydrogens on either side flanking the NO2 will be one environment. The hydrogens flanking the NO2 but are two away are in the same environment. And then there's one on the opposite end, completely on the opposite end of the NO2 will be its own environment. So it completely depends on the substitution pattern for symmetry. Here is some practice for you. Take each molecule given and determine how many signals you would expect to see in a proton NMR for each of the compounds. And then, here's where, just using the number of signals, would you be able to decipher between A, B, and C at the bottom here? Could you take these three molecules and just by signals alone, number of signals, and you were given 3 spectra, could you match the molecule with its spectra just by looking at number of signals? I'll have you guys try that. Next, we want to talk about signal location or chemical shift. As I said before, why does one signal come at 1 ppm and another at just above 2 ppm and a third around 2.5 ppm? Why do they have a different signal at different frequency? Well, I just want to define some areas or regions of our spectrum. Pay attention to the fact that these higher numbers pertain to a higher energy, and these lower numbers in ppm pertain to lower energy. The words that we use the most in talking about the spectrum of an NMR is field, relative to the field strength. So we call the area with the higher ppm values downfield, and the area with lower ppm values upfield. So I would say that these three signals that are shown are upfield. What does this mean? Well, there are two types of proton environments, right? It's kind of like their relationship to electronegative atoms. And what's happening is that when a nucleus is surrounded by electron density, electron donating groups, right? These electrons move in such a way that they generate small local magnetic fields, H local, that oppose the magnet that we've put it in, the instrument. As a consequence to this, the total field strength is reduced, and the nucleus is said to be shielded from the magnet. The way I used to think about this is that electron donating groups are these groups that add electron cloud density. So think about the clouds in the sky. If there are more clouds in the sky, then you're shielded from the sun, right? So this is how I used to remember it as an undergraduate. So the more electron cloud density there was around me, the more I was shielded from the magnet. Okay, and when you're shielded from the magnet, you're upfield. What is going to deshield you? Well, things that pull the electron density away from you, or withdrawing groups, so those greedy atoms that are electron withdrawing groups as opposed to donating groups, right? Electron withdrawing groups are going to pull my clouds away, my electron clouds away from me. And they're de-shielding me so that the sun can peek through, right? I think about it like from clouds, electron clouds, and I'm kind of pertaining it to clouds in the sky. So withdrawing groups pull the electron clouds away, and that thus they're de-shielding us from the magnet. Consequently, the total field strength is enhanced, and the nucleus, the hydrogen, is said to be de-shielded. De-shielded downfield. That was the other thing I used to remember. If you're forgetting which way is downfield, which way is upfield, downfield is to the left, upfield is to the right, and when you're de-shielded, electron density is getting pulled away from you, the clouds are getting pulled away with withdrawing groups, you are more downfield. So, what does this mean? It means that the closer you are to this oxygen, the oxygen is the most electron withdrawing group of the whole thing, right? That is the most electronegative atom. That atom is withdrawing electron density from the things that are the closest to it. So you could argue that the hydrogens on the left and the hydrogens on the CH2 are the closest to that oxygen. Therefore, they are most de-shielded and should be the most downfield. The hydrogens on the far end, the ones that I've just circled, those hydrogens are the absolute farthest away from the oxygen through bonds, and so they should be the most upfield. And you can see that there is one signal that is very upfield and two signals that are very close to each other a little further downfield. So this is making sense, right? The two signal areas, the two environments closest to the electronegative oxygen are the ones that are more deshielded or downfield. We see this in chemical shifts. So where hydrogens are, given their proximity to a given functional group, tends to have some trends, and we can make sense of these trends based on shielded and deshielded protons from what we just talked about. These are not to be memorized. They can be understood, like why were the two environments more downfield than the one, and you can just, relative to one another, you could hypothesize this based on its proximity to the withdrawing group, which deshields the nuclei. But to get down to the precise ppm, no worries. There's going to be a chemical shift chart that I'll give you that you can use as a tool, just like you had an IR chart that you could use as a tool. Roughly, hydrogens that have pretty much no electron withdrawing group at all on it, saturated hydrocarbons, let's say, they're very upfield. Hydrogens, like the hydrogen on an aldehyde or the hydrogen directly attached to the oxygen of a carboxylic acid, they're very, very downfield, deshielded. And you can see all variations in between. Now, the chart that you're going to get in the lab, the chart that you can use on the exam, is going to look like this. So I want you, it's just a matter of getting used to using your tool. There's lots of different NMR spectroscopy chemical shift charts out on the internet, but let's just use this one. And that way, if we always use this, if you're always given this same chart, you'll know how to use it when the time comes. And what's being highlighted here are the hydrogens in specific environments as it relates to functional groups that it's close to. Take a look at, say, a hydrogen. Let's see, a hydrogen right here that's on a CH2 that's next to a carbonyl, as opposed to a hydrogen right next to a carbonyl. Look at the difference between them. This range is what you're looking at for that hydrogen. So a hydrogen on a carbon next to a carbonyl versus a hydrogen on a carbonyl. The ranges vary very differently, right? Because of their proximity to the electron withdrawing group. A hydrogen on an oxygen is in this range, but a hydrogen on a carbon on an oxygen is in this range. They overlap. Okay, so I want you to look at the trends. A hydrogen on a carbon with an OH off of it is in this range. A hydrogen on a benzene ring is over here. A hydrogen on not a benzene ring, but other types of double bonds, just a plain old vinyl one, not specifically benzene, but just a plain old vinyl one, will be in this range. So get used to using this chart, okay? You'll have lots of opportunities to use this chart and use the ranges to figure out whether or not it makes sense. Now, we can again use this shielded versus deshielded to see whether things are going to have more upfield or more downfield strength. Take, for instance, methane. The hydrogens on methane are at 1 ppm. That is very much upfield, just saturated alkanes. What happens when we add a halogen, a very electron withdrawing group? Well, it shifts downfield, right? It goes more downfield to 2.2. If you switch the halogen to bromine, which is more electronegative, it shifts even more downfield. To chlorine, which is more electronegative, even more downfield. And fluorine, which is the most electronegative, is already at 4.3. So you can see that when the carbon has an X on it, a halogen, the hydrogens attached to that carbon will be in a range, Depends on the halogen. So you can see that in this chart here, right? Take a look at this line right here. It's a hydrogen on a carbon with a halogen on it. That halogen could be fluorine, chlorine, bromine, or iodine, and you see that it's got a range. Depends on the halogen. What about the additive effect? Let's keep adding more and more chlorines, as we said above, right? One chlorine on the carbon puts the hydrogens will show up as a signal at 3.1 ppm. Let's exchange one of the hydrogens for another chlorine. So now I have 2 electron withdrawing groups. That is going to de-shield my molecule, my hydrogens, even more. Now it's more downfield, 5.3. So I keep moving more and more downfield, the more electron withdrawing groups, 3 electron withdrawing groups, that proton is going to show up at around 7.3 ppm. Wow. So it matters how many withdrawing groups you have, and it also matters how what type of withdrawing group. The more electronegative, the more de-shielding it becomes and more downfield. So let's go back to our molecule and look at our 3 signals again and use our chart. Okay, so hydrogens, just take one of them. A hydrogen on a carbon next to a carbonyl. A hydrogen on a carbon next to a carbonyl. That's going to have a range. And where are we looking for this? A hydrogen on a carbon next to a carbonyl. Hydrogen on a carbon next to a carbonyl. So it's going to have a range of about 1.5 to 2.5. Okay. So 1.5 to 2.5. That's the same for these hydrogens as well. It's a hydrogen on a carbon next to a carbonyl. 1.5 to 2.5. How about hydrogens that are on carbons next to a carbon next to a carbonyl? Is that even on the chart? A hydrogen on a carbon next to a carbon, so it's kind of 2 removed? No. So we're going to give it in the alkane range because it's a little too far from the electron withdrawing group. So that's anywhere from 0.8 to just under 2. Somewhere around 0.8 to maybe 1.9. Okay, so the hydrogens, we'll call this environment A, environment B, and environment C. It looks like environment A should be the furthest upfield, 0.8 to 1.9. So this signal here must be because of environment A. Environment B and C, I'm not quite sure. They're in the 2, one of them is just above 2 and one of them is just above 2.5. And it could be either one, so I'm not sure which one is which. I can't seem to assign those quite yet. But I've got it narrowed down a little bit. We need to learn a little bit more in order to continue. Okay, so now we understand how many signals. Now we understand why they fall in different locations on the ppm scale, the chemical shift. Now I want to talk about integration. Why are some peaks seemingly bigger than others and some of them smaller? This relates to the number of hydrogens in a given environment. So let's again do this. A, B, and C. We have A, B, and C. 3 environments. Okay? You're gonna see this chart as we move forward. The integration, or the integral, and remember what the definition of an integral is. In math, integration is the measurement of the area under the peak. The area under the peak. These literally are mathematical equations that are done by the instrument. And so the area under these peaks is equivalent to how many hydrogens are in that environment. So if I asked you how many hydrogens live in environment A, you would tell me 3. How many hydrogens live in environment B? And you tell me 2. How many hydrogens live in environment C? You'd tell me 3. So the integration, when the instrument actually takes the integral of these peaks, it's measuring the area under it, and it's going to give it to us in the lowest common denominator ratio. So this is in a 2 to 3 to 3 ratio. And so what you can see here is that I couldn't do this before. I didn't know which one was B and which one was C before, but if I took the integration using the instrument does all the math for me. I see that these are in a 2 to 3 to 3 ratio. I now know that the one more downfield is actually B, and that this one is C, and I already knew this one was A because it's more upfield. Okay. Integration of NMR signals tells us the ratio. We got lucky in this previous one. It happened that the ratio, 3 to 2 to 3, was actually the absolute numbers of the hydrogens in those environments. That's just luck. Sometimes, though, the integration trail that is measured by the instrument, you can see that the trail is in green here. When you measure the integration trail, you can see the trail, it goes up. The instrument does these integral trails. And if all you have on the instrument are these trails, what you can do is measure from the flat part to the flat part using a ruler and get like a number in centimeters. And this ratio, right, will actually give you the integral ratio. So if you look at this, you can see that it's a 1.6 to 7 ratio. And do the math. This is a 1.6 to 7 ratio. Okay, let's get this into whole numbers, right? I think the easiest thing to do is to say, well, if I want to make 1.6 a whole number, right? If I can make 1.6 a whole number, just divide it by itself. So I can take the lowest number and say divide it by 1.6. If I do that to both of them, I'll at least be heading in the right direction. What is that? Well, 1.6 divided by 1.6 is 1. 7 divided by 1.6 is 4.4. Not quite there yet. If I multiply them by 2, I now have 2 here, multiply this by 2, and I have 9. So 1.6 to 7 is equivalent to a 2 to 9 ratio if I want to get it into whole numbers. If you look, the NMR shown is actually for this molecule here. And you'll see that there's a carbon with 2 hydrogens. And then there are 3 methyl groups, all of which are equivalent. So we have essentially 2 signals. All of the methyls are environment A, and then the CH2 is unique, and that's environment B. This is the A is there's 9 hydrogens in environment A, and there are 2 hydrogens in environment B. So this is a 9 to 2 or 2 to 9 ratio. And so notice that the NMR gave it to us in a 1.6 to 7 ratio. The NMR has no idea how many hydrogens there are in a sense, in the sense of giving you the absolute number. It just can calculate the ratio given the integral. So we just get some ratio, and we know that we have to have a whole number of atoms. We can't have half an atom. So we try and find it to its nearest whole number. And so it just so happens that I have 2 and 9. I have 11 hydrogens, but the computer gave it to me in a 1.6 to 7 ratio. I mean, I could have had you could have kept going with these whole numbers. I don't know how many hydrogens I have, but if I was trying to decipher if it was this molecule, at least a 1.6 to 7 is indeed a 2 to 9 ratio, and that supports my claim. This is just more examples showing you that the integration tells us the relative number of hydrogens, not the absolute number. So for instance, In this 1,1-dichloroethane example, the ratio of protons is in a 1:3 ratio, and that's the integral we'll see. Understand, though, that this 2:6 ratio, right, equivalent hydrogens, is also a 1:3 ratio. So if you were just going by integrals, the NMR is not going to tell you whether you have an actual 1 hydrogen and 3 hydrogens or whether you have a 2:6 ratio, right? Or 4:12. Like, you don't know how many hydrogens you're dealing with. You just know the absolute or the relative integration ratio. Let's have you practice some examples down below. How could you use NMR to distinguish between the spectra of the following compounds? Could you do it based on chemical shift? Could you do it based on integration? Could you do it based on the number of signals you would see in each case? What would be the deciding factor that would distinguish between A, B, and C? I'll let you guys figure that one out. You can also practice this one. Here's an NMR spectrum, and I've given you 4 molecules up at the top. Using integration, using number of signals, using parts per million chemical shift, which one is likely to be represented for this NMR? Okay, let's go back to learning the last bit of information we can gather from NMR spectroscopy, and that's the splitting pattern. So the only thing that I haven't talked about yet is why these signals don't look the same. Why are they not just these sharp peaks? Why do they have all these weird splitting patterns? That's called multiplicity. Sometimes people call it splitting patterns, but multiplicity is more of the professional term for it. And this is all based on how one hydrogen, if the nucleus, if it has a neighboring hydrogen on a neighboring carbon, how its spin is aligned either with or against the magnetic field alongside it. Okay, what does that mean? Okay, we can actually use Pascal's triangle back in geometry to think about this. Okay, I'm going to show you, let's start on the right-hand side here. Let's say I have a hydrogen, HA, okay, and it doesn't have, it's on a carbon, and it does not have any hydrogens on the neighboring carbon. There are no hydrogens. Maybe it goes to more carbons, okay? So HA is all by itself in its spin state. So it only has one possibility of how it's aligned with the magnet. And so what you're going to see is just one peak because HA is on its own. If HA, though, is on a carbon, and in the carbon house next door, there's a different hydrogen, right? HB. How could HA align with HB? Well, there are 2 possibilities of equal statistics. It could be aligned with or against. So that's what the arrows are showing. The arrows are representing alignment with or against the magnet. And with the magnet and against the magnet are going to be slightly different in frequency. Thus, they're going to show up very close to one another, but right next to each other in equal ratio, 1-to-1 ratio, right next to each other. And so it could be either spin up or spin down. So we see this doublet. This is what a doublet looks like. How about if we had HA and it was on a carbon, and in the carbon next door, there were 2 hydrogens in that environment. So there are 2 neighbors in the carbon next door. Here are all the statistical possibilities. You could have both of them up. The neighbors could be both up. The neighbors could be both down. One of them could be up and one of them could be down, or vice versa. One of them could be up and one of them could be down. Now, since the chances of up and down from all the statistical permutations are doubled for the up-down scenario and equal in frequency, because it doesn't matter which hydrogen is up, but you have double the chance of having an up-down, then it's a 1-to-2-to-1 chance. And so you see this trend where they're very close in frequency, but not quite the same. So they don't overlap into one signal. They split into this triplet. This is what a triplet looks like. You can see the symmetry of it. Again, I'm going to keep going. What if you have a hydrogen, HA, on a carbon, and next door, that carbon has 3 hydrogens living in it? Okay, what are the statistics here? Well, you've got, they could all be aligned up. They could all be aligned down. You could have 2 up and 1 down, and because there are 3 possibilities of that happening, they add up. They stack, right? There's 3 possibilities. Or you could have 2 down and 1 up, and there are 3 possibilities given that there's 3 atoms. So you get a 1 to 3 to 3 to 1 ratio, and you end up with this quartet, a very symmetrical looking signal called a quartet. These symmetries are because of Pascal's triangle. We see the relative intensities of the signals, and we end up with the number, that's all based on the number of neighbors. And the pattern we see using Pascal's triangle, it basically distills down to a very simple rule called the n+1 rule. Think about n meaning neighbors. So let's put this to practice. Okay, let's go back to our molecule. And what I've done is I've color-coded the hydrogens in different environments. Okay, what I want to do is I want to predict the splitting pattern or the multiplicity for the red hydrogens. I want to know how the green hydrogens are going to split their signal, and I want to know how the hydrogens in blue are going to split their signal. So what I like to do is think about the hydrogens. I never get away from the fact that we're probing the hydrogens. So let's think about the hydrogens as living in a house. Okay, the hydrogens live in their own unique house. And as we mentioned, let's start with the red hydrogens. There are 3 hydrogens, 3 red hydrogens. When those 3 hydrogens, when you put yourself in one of their positions, look on both sides of you. There's only one carbon that lives next door, and that's right there. There's only one house next door to the red hydrogens. And living in that house, this is a zombie home because no hydrogens are living there, so it looks empty. 0. Nobody's there, right? So the red hydrogens have how many neighbors next door? None. So when we apply the n+1 rule, 0 plus 1 is going to give us 1, which means that the splitting pattern is going to be a singlet. Those hydrogens, the red hydrogens, their signal will be a singlet. And it will integrate, the area under that singlet will be equivalent to 3 hydrogens. All right, now let's do the next one. Let's do the green hydrogens. There are 2 green hydrogens. So the number that I'm using right here, that's the integral, the integration. How many live in that house? There are 2 green hydrogens living in that house. It now looks at its neighbors. It's got 2 neighbors, right? The carbon house on the left and the carbon house on the right. Carbon house on the left is the zombie home. It doesn't have anybody living inside it. It's completely abandoned. But its carbon neighbor on the right has 3 hydrogens living in it. So it sees 3 neighbors. Oops. 3 neighbors. So if we do the n+1 rule, we get 4. That's a quartet. All right, so the green hydrogens, their signal will be split into a quartet. Lastly, we have the blue hydrogens. There are 3 of them. So the area under this peak, whatever it's split into, is going to be 3. That's my 3 to 2 to 3 ratio. And the blue hydrogens, when you look at them, you look to the house next door, and you see that it sees the 2 green hydrogens. So the blue hydrogens have 2 neighbors, 2 neighboring hydrogens next door. n+1 rule tells me to add 1. This gives me a 3. So this blue hydrogen environment will split into a triplet. Let's recall what we saw. The blue hydrogens were A. The green hydrogens were B, and the red hydrogens were C. We knew that A was the one most upfield, and if you look, it's indeed a triplet. Right? You can see that triplet because A, when your hydrogen's in house A, you look next door and you see the two at B. Now, we knew that because of integration, we knew that B was this one down here. We can also check its splitting pattern, right? We saw that B, as neighbors go, see the three next door at A, so that's a quartet, and that's exactly what you see here. That's the quartet. And C, when it looked next door, didn't see any neighbors. So 0 plus the 1 gives us a singlet, and that's exactly what we see. It's all coming together. So we've just analyzed this molecule. It's NMR. We understand now why certain peaks are at certain frequencies on the ppm scale, the chemical shift. We understand why some of them have more area under the curve, under the signal. That's due to integration. How many live in that environment? How many hydrogens are in that environment? We understand why we see 3 signals and not a signal for each and every hydrogen because of chemical equivalence. And now we understand splitting patterns, why we see the quartet, the singlet, and the triplet. And that's based on neighboring spinning fields. Here's some practice for you. I'm giving you a C3H6Br2 molecule. Okay? And I can go through this one with you just to help you understand how you can attack these problems. The first thing I would do is I'm given C3H6Br2. Maybe someone did a mass spec and that's what they calculated. C3H6Br2. It's a small enough molecule. I'm going to try and write out a bunch of constitutional isomers for C3H6Br2. Maybe I should try the degrees of unsaturation first. So degrees of unsaturation, I take the number of carbons, right, which is 3, right, there's 3 carbons, times 2, plus 2, and I subtract out the number of bromines, and there's 2 here, right? What does that give me? That's 6 plus 2, 8, minus 2, 6. Okay, now what I'm going to do is I'm going to subtract out, that's this number, that's the degrees of saturation. Now I'm going to take away the number of hydrogens actually in the formula, which is 6, and divide by 2. 6 minus 6 is 0, so 0 degrees is what I calculate. Okay, at least now I know that there are no rings, and there are no double bonds or triple bonds or anything like that. So 0 degrees of unsaturation. Great. Now let's do a bunch of constitutional isomers. Again, we're only working with 3 carbons here. 1, 2, 3. Maybe both bromines are on the same carbon. Maybe one bromine's on one carbon and another bromine's on another carbon. Maybe one bromine's here and one bromine's here, right? So I've got 1, 2, 3 carbons. This would be 1,1 dibromopropane. This would be 1,2 dibromopropane. This would be 1,3 dibromopropane. I don't know if there's any other way to draw this. I feel like I've exhausted it, but maybe I got lucky. Maybe one of these is the NMR shown. I'm first going to determine how many unique environments there are for the hydrogens. So the hydrogen that is at 1, right, there's a hydrogen right here at carbon 1. I'm going to call him A. There's no other one like it. I'm going to call the hydrogens off of 2 B, because I don't see any other CH2s that are one away from a CBr2. And this methyl over on the end, the CH3 at carbon 3, those are unique as well. A, B, C. The ratio is 1, so A to B to C is a 1 to 2 to 3 ratio. I don't think this is looking good for the molecule because I see definitively 2 signals, right, in a 2 to 1 ratio. I'm going to put that one to the side for now. All right, let's go to the next one. We've got a CH3 at carbon 3. There's no other CH3, so we're going to call that environment A. There's a hydrogen at carbon 2. That carbon 2 is a middle carbon with a bromine with a methyl on one side and a carbon 1 on the other. Nah, this is definitely its own thing. And then there is 2 hydrogens at carbon 1. We'll call those C. So again, I'm seeing 3 signals, and I'm seeing A to B to C in a 3 to 1 to 2 ratio. I don't know, the whole 3 to 2 signals things doesn't seem to be jiving with my my NMR. So let's go to this last one. It looks like I might have gotten unlucky. Carbon 1 has 2 hydrogens, and it's attached to a bromine, right? The hydrogens are on a carbon attached to a bromine attached to carbon 2. Notice that carbon 3 has 2 hydrogens. They're attached to a carbon with a bromine attached to carbon 2. So equivalently, the hydrogens at 1 and 3 are actually the same environment. Another way you could have drawn this molecule, 1, 2, 3, and you could see that there's this symmetric point by rotation. So there's 2 hydrogens at carbon 2. We're going to call those B. There's nothing like those. So we're on the right track here because A to B is 2 signals. That's good. There are how many hydrogens living at A? You've got to count all of them. All possible hydrogens living in environment A. There are 4 in total living in environment A. And living in environment B, hydrogens are 2. This is, in fact, a 2 to 1 ratio, which is exactly what I'm seeing integration-wise on this chart. So this is looking good. Let's just double check and make sure that the splitting pattern is accurate. For environment B, how would the hydrogens at environment B split? So you've got to put yourself in environment B and look at your neighbors. And you can see that there's the carbon 1 and carbon 3. So you have 2 neighbors. You have a neighbor on the right and a neighbor on the left, and each one of them has 2 hydrogens living in it. So hydrogen B, N for neighbors is 4, plus 1 equals 5. That's going to be a quintet. Okay, how about environment A? Environment A, put yourself in, make yourself one of the hydrogens as if you're looking out the window. So let me just be this hydrogen here. If I look out the window, I only have 1 neighbor. It's carbon 2, and it's got 2 hydrogens living there. That's your N. Plus 1 equals a triplet. So I should see a triplet and a quintet. This is looking good. 2 to 1 ratio, triplet and quintet. This is a quintet. And this is your triplet. And which one, let's see, does it make sense that the triplet is more downfield? That means the one that is splitting into a triplet. Well, who's splitting into the triplet? A. Let's see. Yeah, A, right here. A is the triplet, right? Are the A hydrogens closer to the bromine than the B hydrogens? Yeah, they are. So because they're closer to the more electronegative group, the A hydrogens should be more downfield, more de-shielded. And this is all making sense. So I now know that this molecule is 1,3-dibromopropane. Phew, it's a lot to take in. It takes practice trying to figure out how to organize your thoughts. I'm going to leave you with a few more examples to cover on your own. Here's a C2H4Cl2 molecule. This is a great problem here. This is a C4H8O2 molecule. This one's tough. Start with your degrees of unsaturation, but I'm also giving you the IR. So this is going to help you understand what type of functional group the oxygen is in. And then you can use the NMR on the right, upper right, to put the pieces together. Okay, a few last points. When you run an NMR, you're going to be able to recover your molecule back. It's not like mass spec where it's destroyed and completely bombarded with electrons and blown to smithereens. NMR spectroscopy, you're going to make a dilute solution of your sample, and you're going to have to make it in a solvent that it dissolves in. Now here's the problem. Solvents are organic molecules too, right? And so you have to pick an organic solvent, like dissolves like, that is polar enough to dissolve your stuff. But here's the problem. If you used chloroform, which is a very polar molecule and dissolves a lot of stuff, it was very popular for many, many years to dissolve things. The problem is that chloroform has a proton of its own, a hydrogen of its own. So if you're using a dilute sample, meaning there's a quadrillion molecules of this chloroform to one of your sample, you're going to dwarf all of the hydrogen peaks, right? So I happen to know, because we just actually talked about it. Here we go. If you remember from this slide here, this last one, this is chloroform. And look at where it falls on the ppm scale, 7.3, 7.25 to be exact. So if I was running a sample in an NMR and I was using chloroform, okay, here's the ppm scale. You're using a quadrillion, bajillion, like super large number of the solvent because your sample is dilute in there. So there's only one, a few molecules of your stuff, and then a bajillion of the solvent. This is the solvent you're using to dilute your sample. Well, at about 7 ppm, there's going to be a huge peak. Huge. Okay? Your stuff, you might not even be able to see it. It'll just look like a little noise on the baseline. And you just will not see it. Your solvent will dwarf your desired signals. Okay? So, how do we do that? How do we dissolve it in something and not see only the solvent when we run the NMR, right? Well, what we can do is buy a little bit more expensive compounds called deuterated chloroform. Now remember, the NMR is probed for proton, H1. H1 NMR. H2 NMR is called deuterium, or D. We actually use D as deuterium. That is the H2 isotope, right? So that isotope is completely blind. It cannot be seen by the instrument. Just like we couldn't see the carbons. We weren't looking at the carbons. The probe was not looking. It was not tuned to look at carbons. It was only tuned to look at the H1 isotope. So if you can actually buy deuterated chloroform, that deuterium is completely invisible to the instrument. You can't see it. Now, chloroform D, when we purchase a bottle of chloroform D, it's not pristine. It's probably like 99% chloroform D, and there's going to be some residual chloroform. So just a little bit of chloroform where some of it has the H on it. So what ends up happening is that you always have to be cognizant of the type of deuterated solvent you use, because there's always going to be some residual from the solvent. So you're probably going to see a little peak at 7 point, but all of your other peaks will show up nicely. You know, you'll still see whatever peaks you're aiming to see on your spectrum. But this peak over here, you might say, why did she ignore that peak at 7.25? Well, I ignored it because I knew it was just a little bit of residual chloroform. Most of what I used was chloroform D, but the bottles are never perfectly deuterated, and there's always a small percentage of the protonated chloroform form. And we have charts that you guys can look at depending upon what solvent was used. Oftentimes my students will run, they'll have just freshly cleaned their NMR tube with acetone, and they don't dry it well enough. And so when they run their sample, it looks like one peak for acetone. They're like, what is this stuff? It's pure, whatever it is. I don't know what it is. And I say, did you just wash your NMR tube? And they go, yeah. And I said, did you rinse it with acetone? Yeah. You didn't dry it. The only thing that the NMR is picking up is the acetone that's still sitting in there. So they ended up diluting it in acetone, which has tons of hydrogens all over the place. And that's all they ended up seeing on the NMR. So you always have to be very cognizant of, you know, what you washed your glassware with, because the NMR is going to be sensitive enough to pick it up if you don't dry it properly. Or what solvent did I use as the diluting solvent? If it's deuterated, there's always, whatever deuterated solvent you can use, D2O, which is heavy water. Any deuterated solvent should work as long as your stuff dissolves in it. But you have to be cognizant that it's never 100%, and you might see a residual peak due to the solvent of choice. The last slide I will show you on NMR before I turn you loose and have you practicing yourselves is what happens to hydrogens that are on heteroatoms. And I'm not going to get into this too much, but I want you to some degree ignore them. I call them the teenagers of being in the neighborhood, right? I have teenagers at home, and I know that sometimes they are oblivious to who our neighbors are. You know, who's that? They'll say. I'm like, that's our neighbor. You don't know that? No, I didn't see them before. I was like, okay. And sometimes our neighbors are oblivious to the fact that I have teenagers because they're never home. So hydrogens on heteroatoms like oxygen, nitrogen, sulfur, things like that. Remember that these hydrogens on heteroatoms are often involved in hydrogen bonding interactions. Man, those hydrogen bonding interactions, right? Hydrogen bonding interactions. They interact with other molecules that have those dipoles, right? Especially when you're talking about having a hydrogen bonding interaction with the deuterated solvent. So what happens is that you can get something called fast proton exchange. The oxygen is attracted to the deuterium of your solvent. And what would happen if they exchanged and it became OD instead of OH? Remember what I just said, deuterium is invisible to the instrument if it's probed to hydrogen. So if it exchanges quickly, it's like it doesn't exist there. But sometimes it is there, and sometimes it isn't there because it's in a fast proton exchange. That's what's written right here with the solvent. So sometimes it's there, sometimes it's not. It's like a teenager. So if you have the ability to hydrogen bond like hydrogens on heteroatoms do, it exchanges. So even when you're there, you're not there long enough to sort of feel the effect of the magnetic field of your neighbors in the same way. So you don't split. There's no splitting. So the protons bonded to carbons split each other, but the hydroxyl proton, like the one here, because it's never home long enough to look at its neighbors, ends up not having a splitting pattern. Even though next door, see the carbon next door has two hydrogens? It should be a triplet. But that singlet that we see is due to the teenager hydrogen on the heteroatom. It's exchanging, it's in and out. It doesn't have time to look at its neighbors, so I don't know, I don't see any neighbors. So it just gets a singlet. That's the way I like to describe it. So the ones you want to pay strictest attention to, the ones that are going to lend some connectivity, puzzle pieces for you are the hydrogens on carbon. Stick to those. Understand that sometimes you see them. You may even see a spectrum that has an alcohol in it, and the hydrogen, because it's in the fast proton exchange, not only does it not split, sometimes you don't even see it, or it's like this little, you might even see it as like a little blip. And you're like, what's that? It's not worth looking at. Look at your strong, sharp, split peaks, right? If you see a singlet, okay, you can attribute it to the alcohol, but maybe work with the IR to validate that you do indeed have an OH stretch, and then say, oh, that must be the hydrogen of the alcohol. So don't worry too much about hydrogens on heteroatoms. Pay stricter attention to the patterns that you see for hydrogens on carbons. This can be tricky, but practice makes perfect. Try to do as many problem-solving NMR problems as you can.